Okay, so this, like I said, this is just going to go through every one of the problems on the homework in the preparation for Wednesday's exam. So we start out with the sort of the second row diatomics, the MO diagrams for all of those. And first of all, let's just start from the very basics. Do you know what's being represented by each of these squares? Like this piece right here, all these lines right here. That's the MO diagram. That's the energy levels of the molecular orbitals. In the middle of, you got the atomic orbitals here, they combine to make the molecular orbitals, and that's what's being shown in every box. Okay. So you can work your way up. This bottom one is going to be what designation? Yeah, sigma. Yeah, and then this one, sigma star. What about these two degenerate ones? Pi. This one. This one, yeah, sigma, and then those are the pi star and then sigma star. So it goes in that order. And then after we get past nitrogen, notice they swapped order. And so this sigma is now below the pi for oxygen and above. So like chlorine and all of those, if you were to make something, if they were calcium or whatever, all of those above nitrogen. So when you get to oxygen, they all look like this. Okay. What's the term we use for this nitrogen and below? What's causing that sigma to be higher or those pi's to be lower? It's called sp mixing. So there's some mixing of the s and the p orbitals because the atoms are so close together. Those orbitals, the 2s and the 2p, are close enough together in these first few elements that you get some p character in the s orbitals and some s character in the p orbitals, and so then you have a different ordering of the molecular orbitals. Okay, so that's good. So then we can ask questions about these different diagrams. So which second row diatomic has the shortest bond length? So looking at this diagram, how would you determine the bond length? What would it be in terms of ranking? What would it be related to? Highest bond what? Order. Yeah, highest bond order. So you go through and calculate the bond order for all of these. So this, let's just label this one, we'll label all of these. So if you have your notes, you can do what we just did. And so then we'll just remember the bond order is, can I just do n star minus n? Wait, it's n minus n star, sorry. So let's do it for oxygen. So for oxygen here, so we've got 2, 4, 6, 8. So 8 minus, here's 2 anti or 2 star electrons, and here's also 2 more. So minus 4 over 2. So 8 minus 4 is 4, divided by 2 is 2. So that's a bond order of 2. So we could do that same calculation for all of these. So let's just write out the bond orders. So this one is a bond order of 1. It's got 2 in the bonding, 0 in the antibonding. This has 2 and 2, so it's a bond order of 0. Okay, then beryllium or boron, so diboron would be a bond order of 1 because we get 2 more electrons in a bonding orbital. Carbon, you have 2 more electrons in a bonding orbital, so it's a bond order of 2. Nitrogen, you have 2 more electrons in a bonding order, so it's 3. Then oxygen, we start adding electrons in the antibonding orbital, so it knocks it down a notch. So that's back down to 2. Fluorine, we're adding 2 more electrons in an antibonding orbital, so that's down to 1. And then neon, we've added 2 more in the antibonding orbital, so it's back down to 0. So it's a maximum bond order at nitrogen, the N2 at N2. And so that's going to be the shortest bond length. Okay, then we start doing cations and anions. So let's do this one. Oxygen 2 minus. So let's do isoelectronic. E. So which one is this isoelectronic with? So here's oxygen. If I put 2 more electrons in there, I do this and I do this. And it looks the same as F2. Okay, so we'll do, this is the same as F2. So B2 plus. Well, we've got B2. B2 plus would be close to beryllium, but it would just have 1 electron in there. So it would be like, if we're going to take away an electron, where are we taking it from? We're taking it from a bonding orbital. So we're weakening that bond. And so this has a bond order, F2 has a bond order of 1. B2 has a bond order of 0.5. Because you see it's going to have, when you subtract out the antibonding electrons, you only have 1 electron left, and divide that by 2, you got a bond order of 0.5. Here's lithium 2 plus. So lithium 2 plus, we take away those 2 electrons. It's going to be the same as helium 2, okay, and He2 is going to have a bond order of 0. Okay, so this is going to be a bond order of 0. N2 2 minus. So here's N2. We add 2 more electrons. Okay, it's going to look just like oxygen. So that's going to be equal to O2, which has a bond order of 2. And here's F2 2 plus. So F2 2 plus. It's going to be isoelectronic with O2, which is going to have a bond order of 2. That's kind of a weird problem that I give you. Let's see. Because we have 2 right answers. Have y'all done this one to know which one is right? Yeah, I think it's N2. Okay. Yeah. Okay, I need to go in and correct this homework because this is ambiguous. Or did I correct it on the one that you have?
I don't know. I can check the grade. I don't even remember what I put.
Yeah. When was this one due? Was last Saturday or? Oh, wow. Okay. Well, it's good review nonetheless, right? Yeah. Yeah. So, yeah, let me see. Well, we can go look, see what's posted, but do you see what I'm doing? I'm looking to see what they're isoelectronic with, and then I'm picking the one with the highest bond order to show the smallest bond length. Yes? Yeah, you might be able to say, well, but the other side of things is that fluorine has more protons, and so it's going to tend to want to repel. And so, yeah, I mean, I can make an argument for both N2 2 minus being shorter or F2 2 plus being shorter. So, yes.
If a problem like this was asked in the exam, would you give us that schematic above too, or no?
Yeah. So, what's that? Okay. Yeah. So the exam will be very similar to this in terms of what's given. Like an MO diagram, we'll see that MO diagram on O2 was given, and you asked a lot of questions about it. So that, if I have you generate an MO diagram, then you're doing the drawing. But then if I'm asking you questions about one, I have to draw it. So I can put little boxes and things, like the little rectangles that I put on there, so I can ask you questions about it, so that there's an absolute clear answer. Because I want to be able to give you an absolute clear answer, and I say that right after I give you one that's ambiguous. But I'm acknowledging this is a mistake, right? This isn't something I'm doing to you to like get you or anything. Yeah. I think I discovered this before in the past, and I went and it actually changed the homework. So we'll see. Okay, so then let's see. Here's the force constant question. Okay, so let's go on to the third one. Which second row diatomic is paramagnetic of these options? Okay, so what does paramagnetism give you, or what is it caused by? It's these unpaired electrons. Yeah, so unpaired electrons make the electron cloud magnetic. So that's paramagnetism. And so O2 and B2 would be paramagnetic in their neutral molecules. And so looking on here, we don't see B2, but we do see O2. So it would be this one. Okay. And then which second row diatomic has the highest vibrational force constant? So this right here is also going to be related to bond order. So bond order is the shortest bond length, okay, and also the highest vibrational force constant. And that's typically given the K. So as we can write it like this: as bond order goes up, R goes down, right? It gets a smaller bond length. As bond order goes up, K goes up. And as bond order goes up, the vibrational frequency goes up if they're similar masses. Okay. So this one right here, this B2 2+ with a bond order of 1/2 should have the longest R, the weakest K, and the lowest vibrational frequency. Again, taking out the effect of mass. Okay, so it's a lot of talk on 4 questions. We can better move on. Okay. All right, so now we get the coordinate system. We got a molecule here. We're talking about the pi bonds. Sometimes I ask you to draw the pi bonds on here, so let's go ahead and practice that too. So if I want to draw the pi bond on this molecule system, let me simplify it by just drawing it like this. It's weird. Why is it doing that? Okay, so I'm going to draw the top of the p orbital on those carbons. Why is it disappearing? Y'all seeing that? Okay, so that's the top of the, and then we do the banana on the back, or the half moon, and we shade that. If it's shaded in the back and not shaded in the front, they're in phase with each other. So that's the pi. You can draw the same thing for the pi star. But now the half moon in the back is shaded on one of them, but not the other. And the front is shaded here. So that's the pi star. You think you're better at understanding these pictures now? Good. I see some nods. That warms my heart. Thank you. Okay. And so then I ask you all kinds of questions about the symmetry of these things, and so we can look at the character table. I nearly said periodic table. The character table, and find those different symmetries, and looking at the coordinate system. So what's the symmetry of the carbon-carbon pi MO? So that's drawn right there. And we can look at this axis here. The z-axis is coming out of the plane of the board. Okay, so it's coming towards you. And you can see that, remember, the shading is the expansion and contraction of this orbital. And so it's coming out and going into the board. So it's coming out and going back and coming out. So the oscillating electron cloud's doing this. And that's along the z-axis. So it has the z-axis symmetry. So we come over here to the character table, we find z. It's B1U. come back over to this row, and so then we come up and find that. So that's this one. Okay, then the pi star, again, the shading is the expansion and contraction of the electron cloud, and so in this case, it's doing this. One of them is coming forward while the other one's going back towards the along the z-axis. But that's not z symmetry because it's kind of split, right? It's got z character, but it's also got x character. So if you look at it, you know, see how my hands, if it's like here, it's like small and big, it's going left and right, but it's also going forward and back. So left and right is x, forward and back is z, so it's x times z. So we go find xz right here, B2G. Okay, so then what's the symmetry of y polarized light in this coordinate system? So just random, just ask you about y light. So we go find that. Here's y, B2U. What type of light would be absorbed in a pi to pi star transition? So this one is, let's just draw this this energy level here. This one is B1U, and this one is B2G. Except for Y. Okay, so this is the pi. This is the pi star, and then this Y polarized light would be the light that we're looking at in terms of it coming in, would be B2U. And so we could do all of those different transition dipole moment integrals to see which one. And so here we have what type of light would be absorbed in a pi to pi star, see above. And so, I mean, just because I asked about Y doesn't necessarily mean that that's the one that's going to be absorbed. So let's go ahead and see if the Y polarized light, do we have that on the next? No. Okay, so let's go ahead and do all of those. So let's do this situation here. So we've got B2G here, B2U, and B1U. Very first thing you want to check, if you have U's and G's, just to see if the U's and G's work out, okay? Because if you don't have a G at the end, you can't have top row. So you can just look at the U and G rules and know that, you know, if U times U gives you what? Gives you a G, and so then we would have a G here, and G times G would give you a G. So at least with the U and the G rules, this is possible to be allowed. Let's do now the B1s and B2s. So there we've got to have the B1 times B2. Here's B1, there's B2, so it gives us a B3. So this one would be B3, G. Bring the B2G down. Okay. And then this is B2 times B3, so that's B1. So that's a problem. So that's not top row. Therefore, not allowed. By symmetry. Okay, so it's not Y polarized light, so we can mark through that one. One way to figure this out is we need to have something. So here's B1. We need a light that's going to multiply by B1 and give a B2. So we can kind of do this knowing that that's what's going to happen. Here we had B2 times B1, and that gave a B3. And B3 and B2 are never going to produce an A, right? We need a B2 here. So what times a B1 will give a B2. We can look at this. B3 times B1 will give a B2. And so we need a light that is B3. So X polarized light is B3. So let's do that one just to make sure we, we're right. So the top level is B2G. We need a light that's B3U. That was X light, X polarized light. And B1U is our lower state. So B3 times B1 is B2. U times U is G. And now we have B2 times B2. Anything times itself is going to give top row, or A. And I think this just has A. It doesn't have A1. Yeah, it's just A. So B2 times B2 gives A. G times G is G. And so this is not equal to 0, therefore allowed by symmetry. So it's going to be X polarized light. But did you see how I did the logic? That way we didn't have to do all 5 of those. Okay. And it's on the video if you want to go back through that again later. Okay. All right, let's look at this crazy MO diagram. I'm drawing all the little pictures in using ChemSketch, which is kind of nice. It's got the atomic orbitals. Took me forever. It's easier to draw by hand, but my handwriting is terrible. So this is at least nice to look at. Okay, so up here at the top, how many valence band photoelectron peaks are predicted by local bond theory? So for the O2 molecule. So let's just draw the straight Lewis dot structure for O2. And so what we're doing is local bond theory. How many types of question is how many types of electrons are there? Okay, so we have the non-bonded pairs. Those would be different than electrons that are, say, in a sigma or a pi bond. And so that would be 1. And then we have the sigma bond, which would be a second type of electron. And then we have the pi bond, which would be a third type of electron. So 3, what does this say? Photoelectron peaks. There's always a lot of folks that are confused by that, but I want you, if you're confused, ask your questions. I'm trying to make it pretty simple. You just draw the Lewis dot structure, and whatever types of electrons you have, each one of those would give a different energy. And if you hit that with UV light or X-ray light, you would see electrons of that particular binding energy come out with a certain kinetic energy. And so it's the photoelectron effect that we're using to probe the structure of the electron cloud. So what is it that, okay. Was it the sigma bond, pi bond thing? Okay. So yeah, it's just you draw the Lewis dot structure and you figure out how many different types of electrons you have. Triple bond would classify as pi bond. So let's, like, thinking about acetylene. Okay, we've got CH bonds, and so that would be, 1 type. And then we have the sigma bond here. That would be a second type. And then we have both pi bonds. And that would be a third type. And so for acetylene, there would also be only 3 types of electrons. So you would predict, if a local bond theory were true, you would have 3 different energies. You hit that with so with the way photoelectron spectroscopy works, you pick a really high energy photon like a UV source or an X-ray source. X-ray source gets core electrons, and so that would give us the 1s electrons on the carbon. But the UV, a deep UV source would give us the you hit it with a fixed energy of incoming photons, and then you look at the kinetic energy of the electrons that come out. And the deeper those electrons are in the electron cloud, the closer they are to the nucleus, the slower they come out of the molecule because it took more energy to pull them out. And so they come out with a small kinetic energy. And then the ones that are further from the nucleus come out with quite a lot of kinetic energy. So it's a way to kind of penetrate the electron cloud and see how close the electrons are to the nucleus, because that's what's holding on to the electrons. So we can really get an energy depth of each of the electrons. So if local bond theory were true, we'd get 3 peaks out of acetylene, we'd get 3 different kinds of peaks out of oxygen, but we would have 3 peaks. But here's the molecular orbital diagram for oxygen. How many peaks would we get out of this? So you just count up the occupied orbitals. So 1, 2, 3, 4, 5. So 5 photoelectron peaks predicted by the MO theory from oxygen. So very different results. And you can go to the spectrum and see, is it 3 or is it 5? And you see that it's 5. Okay. Yes?
If we don't have the MO diagram, how do we know how many peaks to...
You'd have to draw it. So you'd have to make up the MO diagram so that you would see how many occupied orbitals there are. Yeah. And it's not just the star, it's not just the bonding orbitals, it's the antibonding too. So it's all the occupied orbitals would give you a peak. And the one that only has, it's half filled, right? These up here, there would just be a smaller peak, but it would still be a peak. So it's got fewer electrons in it, so it'd be a smaller peak. Okay. So now let's ask questions about this. So we got boxes, 1, 2, 3, 4. Where's 4? Is there a 4? 1, 2, 3, 5, 6, 7. That's crazy. Who made this thing? Okay. All right, so let's see. Refer to the number of rectangles in figure 4 or figure 1. What molecule label should be in rectangle 7? Okay. Rectangle 7. It's a blank MO diagram. Okay. So it's just asking you, is this oxygen? Is it oxygen cation, oxygen anion? What is it? So we're looking at the number of electrons. We come in with 6 valence electrons, so we should have 12 total. So we got 2, 4, 6, 8, 10, 12. Okay, so it's oxygen, no charges. So it's O2. No, not a cation, not an anion. If we only had 10 electrons, it'd be O2, 2 plus. Okay, that kind of thing. Refer to the number of rectangles in figure 1, which orbital label should be in rectangle 1. So rectangle 1. So what is this thing? What would we label this? Yeah, the 2s. Why is it not the 1s? Yeah, but oxygen has a 1s. Where is it on this diagram? It's what? It's way down close to the nucleus. And so it's just down, if this was the MO diagram here, then the oxygen 1s would be down here. Okay. So it's energetically very low, and so it's just not shown on this diagram. So just want to emphasize that the MO diagram is only the valence electrons. So the core electrons are not shown. They're there, they're just really low in energy. So if you were to show them on the same scale, remember I did carbon monoxide, and I showed the whole thing, and the valence levels were way up here, and you couldn't see the difference between them because I could see the 2s and the 1s. We'll see carbon monoxide, yeah. Just the 1s orbitals for the oxygen and the carbon. And so then once I zoomed in to just the valence band, you could no longer see the 1s orbitals. So they're just way up at the top. That's why we can use UV light to get the MO, the molecular orbitals, but we have to use X-ray light to get the core because they're much lower in energy. Okay, so let's So the 2s is the answer here. Refer to the numbered rectangles. Which symmetry label should be in rectangle 1? Symmetry label, rectangle 1. Okay, so this would be the 1s orbitals. And again, the s orbitals are going to be top row. Okay. So top row would be A1G for this molecule. So we would come in here. It would be A1. Let's see. We don't have the A1. Don't have the A1G on here, but it's A1. Okay, refer to the numbered rectangles, figure 1. What Cartesian label should be in rectangle 1? Okay, so this is a sphere. For rectangle 1, that's the 2s orbitals. And so you're looking at the character table, you're going to see all of these squared ones, you know, x squared, y squared, z squared. It's not exactly the equation for a sphere, but it's close. It's similar to. Okay, which orbital label should be in rectangle 2? So here's rectangle 2. We're going to label that orbital. So we're labeling the orbital with sigmas and pi's. And so what would this one be? Yep, 2 sigma star. So that's here. What symmetry label should be in rectangle 2? So we come up here, rectangle 2. I guess we need to know the D infinity H character table. So let's go find one of those. Got one here. Here we go. So D infinity H, this has Z symmetry. So Z symmetry gives us A1U. So we need to go back, and it would be A1U. How did I know it was Z symmetry? Let's look at this. So here's the Z axis. It's the axis of the molecule, the principal symmetry axis, that C infinity axis. And this is oscillating. The 2s orbitals are oscillating like this. You see the left and right motion of the electron cloud. And so then that's going to be along the Z axis. So it's Z symmetry. So it's A1U. Okay. And then which Cartesian label should be in rectangle 2? I just said it should be Z. I typically find the Cartesian label first and then go to the character table and find the symmetry. Yeah, so I recognize that it's Z symmetry, and so then when I go find Z, I know that it's A1U. Okay, which orbital label should be in rectangle 3? Here's rectangle 3. These are okay, so this one is labeled here. That's the 2px. This is the 2pz. So we're talking about the one labeled with this guy here. The only one left is 2py, so it'd have y symmetry. Page. Okay, so y symmetry. So we need to go to that character table and find it. So y symmetry, and then this is the particular character table. X and y are doubly degenerate, so it's going to be E1U. So it's going to be the same as the X one. You can see that here. So X is E1. I don't have the U's and G's on this one. Must be a copy and paste from carbon monoxide or something. But yeah, it'll be 2py E1U. And then rectangle 5. What's the orbital label for rectangle 5? Okay, so here's one of those that has that plus minus pattern. So plus minus. You just need to figure out what plane defines that pattern. And so in this case, that's the plane of the paper. So that's the XZ plane. So this is going to have XZ symmetry. Everybody get okay? Are you okay with that? Yeah. Okay. And so we find XZ symmetry in the character table. Here's X. Let's see, XZ. That's weird. There's a mistake in this character table. Look at that. This is XY, and this is XY. I'm gonna take a chance and say that this is the one that's mistaken. We'll look it up, but this is YZ. XZ and YZ should be paired.
The answer choice doesn't have E2Gs.
It doesn't. Okay.
So E1.
Okay, so that's the man. I need to go through this with a fine-tooth comb. Okay, so that's XZ symmetry. So we go find that's E1G. E1G, and what is the? Oh, that was the pi star, right? That was pi star. Okay, and then rectangle 5. What's the Cartesian label for that? We determined that it was XZ, YZ. It's this one. And then what's rectangle 6? So what orbital label should we have for rectangle 6? It's going to be, not everybody at once, sigma star. Very good, because we have that node that breaks the bond. So that's how you know if there's star. See here, this node breaks the bond. This has a node, but it doesn't break the bond. It contains the bond, and that's the typical of a pi or pi star. There's a node that contains the bond, and the way you tell between pi and pi star is if there's a node that breaks the bond as well. So whenever there's a node that breaks the bond, it's a star. So that's how we would know that it's antibonding. So what was sigma star? Okay, what's the symmetry label of that one? That one's going to be Z as well. If you look at it, it's got a little extra curvature to it, but it's still oscillating right and left. Okay, and so then that's going to be Z symmetry, which is going to be A. What did we determine that it was down here? Was A1U. They're just from bottom up. So, and there's not really a huge scheme for that. So sometimes they're, so this is one way to do it. So this is 1 sigma, 2 sigma star, 3 sigma, 4 sigma star. Okay, and then the pi's, this would be, I guess, 1 and, I don't see that it's listed. Yeah, here it is. Yeah, so one pi is in the XZ plane, 2 pi is in the YZ plane. This would be 3 pi star. And this is 4 pi star. It's just labeling them sort of in energetic order and starting over with the pi's. So that's one way to do it. So the way I would expect you to do it in this particular diagram is just to kind of look at the diagram and say, oh, okay, I see it's 1 sigma, and then we have 3 sigma, so this one must be 2 sigma. Sometimes they will label them 1 sigma, and then that same kind of sigma star, they'll call that 1 sigma star, and then they'll do 2 sigma, and then the star for that one will be 2 sigma star. So I've seen it both ways. So there's not a real strong convention either way on that. So you have to just be consistent within the diagram. It's not a satisfying answer when I say there's really no convention for that, right? So, but that's what I've seen. So rectangle 6, we came up with A1U because it was Z symmetry. Okay, here's the Cartesian label. Okay. First of all, we need to identify the HOMO and LUMO, and then we need to determine their degeneracy. So we can come up here and look. So where's the highest occupied molecular orbital? Yeah, really 3 and 4, the pi stars. So it's the pi star setup here. That's the highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital. And I would say fully unoccupied, right? It doesn't have anybody in it. The highest occupied molecular orbital has some chairs, some open seats, right? But it's occupied. It has somebody in it. Okay, so there was some confusion in the past where they would also label this the LUMO because there's an open spot, right? That's an unoccupied spot, but that orbital has an electron in it. So we're going to call that occupied. It's not full, but it is occupied. Okay, and then this is the lowest unoccupied, which means it doesn't have any electrons in it at all. So that just in terms of clarity, these are the definitions of the HOMO and the LUMO. And the degeneracy of the HOMO is 2, because you have 2 equal energy levels. And then the LUMO has a degeneracy of 1. It's looking at this diagram, so like this is a degeneracy of 3 right here. They're equal. How many orbitals do you have that are equal energy? Yeah. So that's what we mean by degeneracy. Okay, then we did the bond order for this molecule. We've done that a whole bunch of times. And it was 2 for oxygen. What would be the bond order of this molecule after it gained 2 more electrons? So we can look at that and we can see, does it strengthen the molecule or weaken the molecule if we put 2 more electrons on this? Where are they going? They're going into a pi star. So it weakens the bond. So if we put 2 more electrons in there, we're going to cancel out a whole bond. Think of it that way. It's an antibonding orbital. We put and 2 bonds counts as 2 electrons count as a bond, right? So if we put 2 more electrons in there, we're actually taking away a bond because we're putting them in an antibonding orbital. We're weakening the molecule. And so that would be the bond order of 1 if we put 2 more electrons in it. If we took 2 electrons out, we're pulling electrons out of an antibonding orbital, and so then we're making it stronger, and it would go to 3. It would go to a triple bond. It would be isoelectronic with nitrogen. All right, what's the symmetry setup for the HOMO to LUMO transition? So let me just go ahead and let's see, does it say? It doesn't say which type of light, but let's just go ahead and set it up. So we have the LUMO light and the HOMO. So we go put the symmetries in there. So the LUMO is A1U and the HOMO is E1G. Okay. So if we want to make it one that's allowed, what do we need? We eventually want to get something that's going to be A1. So what times E1 will give us something that contains A1? E1. Okay, so we need light that has an E1 because E1 times E1 is going to give us A1. It's going to give us a lot of stuff, but it'll contain A1. And then does it need to be G or U? Y'all were pretty fast with that. Some said G, a few said U. We've got a G over here, and we need it to give a U so that it can have a U times a U and give a G again. Okay, so it needs to be a U. So U times G would give us a U, and U times U would give us a G. So we want to have all the U's cancel out. So we can go to the character table and see if there's anything that's E1U, and there is X and Y light. So X and Y polarized light would give us E1U. So that's X, Y light. So light polarized in the X or Y direction would cause this HOMO to LUMO transition to be allowed. Let's go ahead and verify that. So E1 times E1 gives A1 plus, and it's got 3 things in it, so we need to go to the direct product table here. Well, A1 plus A2. Yeah, A1 plus A2 plus E. And then G times U is U. So these would all have U's on them. And A1 times all of those is going to give us those things back. And so we're going to end up with this result. A1G plus A2G plus E1G. And so this is going to be the setup here. We had A1U, E1U, E1G. So this was A. And then the result here is 1G, A2G, E1G. So it's this one. And so in answering this, we had to come up with the XY polarized light was the light that would allow the HOMO to LUMO transition. And then the pi to pi star transition, we could do the whole thing again. Let's see if we thought we did that one. We did that one in this molecule. Okay. Okay, so the pi to pi star is E1U to E1G. Okay, so E1U to E1G. So what goes in the middle here? Well, we don't want to get rid of the E1s. We don't want to mess that up. Okay, so we want an A1 for that. So A1 times E1 is going to be E1, and then we'll have E1 times E1, which will give us an A1. So this is good. And then we have one U over here and a G over there. So we got to cancel this U with a U. So we would put a U there, and that would give us our allowed transition. So this would be E1, G, and that would give us our A1G. Okay, so we need to look up A1U in our character table and see if there's a light that associates with that, and sure enough, it's Z polarized light. So that would cause our HOMO to LUMO transition in this molecule. Yes?
I think you did right just now, but on the frequency
D. A1, 2. I did this from memory. This piece right here, E1 times E1, this might be a 2. I looked for the direct product table for D infinity H. I don't have it right here in front of me. So let me go to the notes and see if that's correct, because E1 times E1 might be E2. Is it a 2? Yeah. Okay. So my memory was wrong. Okay, so it was this step right here. This E1 times E1 should have been a 2 right here. And then that means that it's this one. Okay, so we're kind of out of time. But did I get through everything? Yeah, I did. Okay. Okay. Well, hopefully that's a good review. It'll be very similar to this. So hopefully I want to see some good grades. Yes?
Are we going to do short answers?
No, it's good. Yeah, there might be one where you have to draw, because I want to see you draw it. Yeah. Yeah, it'll be all of these plus like a drawing one. Okay? All right.